Welcome our lecture. My name is Valentina Domingues. I'm from Instituto Superior de Engenharia do Porto, Polytechnic do Porto. The title of my lecture is Eco-Friendly Bioplastics and Biocomposites, Part 2, Biocomposites from chestnut industry waste, production and characterization. This lecture is included in the AGRIMA project, Agri-food Waste Management for Sustainable Bioeconomy through Higher Education Curricula and Upscaling. AGRIMA aims to foster universities' capacity building for the green transition through innovative practices and higher education curricula updating in Agri-food Waste Management for the circular bioeconomy. AGRIMA addresses advancing pedagogical methods for industrial agri-food waste valorization based on business academia synergies and integrating citizen science in bioeconomy enhanced waste valorization as a means of civic engagement and environmental advocacy. The partners are from 4 different countries, Portugal, France, Greece, and Serbia. Port's history is deeply intertwined with the Douro River, as you can see in the picture, which has shaped its development as a trading port and a key gateway to Portugal and beyond. The city's strategic location at the river's mouth has facilitated trade, commerce, and naval activities since Roman's time. Here you can see some pictures from our city port. Right? It's a little slow. Okay. Instituto Superior de Engenharia do Porto, our school, is one of the top schools of technology in Portugal and has been pioneering education and research in engineering since 1852 and offers a wide range of programs in different fields of engineering with more than 60,000 students. I'm also a researcher at the LACV, the first one, Associated Laboratory for Green Chemistry of the Network of Chemistry and Technology, Requinte. That is the Portuguese Research Center for Sustainable Chemistry. I'm a researcher in contaminants evaluation, several matrices, biocomposites, biomonitoring, food composition and food safety, and phytotoxicity. For an overview, the production area has more than doubled in the last 20 years, according to the Food and Agriculture Organization data. Here I showed a graph of the top chestnut producers in the world account for 99% of the global production. West China stands out in the first place, while Portugal is in the 8th place. You can see in the left a picture of the birds in the chestnut tree, and here the fruit inside the bars, as you can see. About consumption. In Asia, the consumption in Asia is around 2.5 kilograms per person. In Europe, 0.5 kilograms per person. In the United States, around 0.05 kilograms per person. In Portugal, chestnuts are considered a delicacy and are prepared in a variety of traditional ways, especially during the autumn months and on St. Martin's Day, when they are commonly roasted over open flames, like here in the left in the streets. We sell the chestnut in old paper like you see in the middle of the picture, or you can consume boiled with spices or used in savory dishes and sweet desserts. We have a lot of losses during the production chain. So the production chain, since farming, processing, distribution, retailing until home, we have a lot of losses. Around 40 to 50% of chestnut are lost to infestations, rot, and processing residues. Around 12,000 of tons, that's the estimated annual weight loss. And the estimated annual economic loss is around 24 million euros. So, taking account all these losses, we apply for funding for a research project. The project is ChestFill, that aims to do valorization of solid residues from processing of chestnut. And the aims of the project is bioplastic and biocomposites production, and also obtains bioactive compounds using sustainable extraction techniques. So we have a founding project. The researchers, the team members from Oporto are myself, I'm the PI of the project, Professor Cristina Matos, the researcher Helena Surra, Professor Olga Freitas, the researcher Elsa Vieira, and two grant holders, Samara Rodrigues and Simão Silva. About the industrial processing. In the farm, the chestnuts are catched, here in the left, and normally the bird stays in the field. Then the chestnut fruit are transported to the company in the open bags to providing ventilation, and then go to the company. In the company, they are properly washed. After wash, they are properly labeled and properly stocked in the freezing. To obtain fruit without shells, it's necessary to a source of heat, and then automatically there's a machine to take out the shells of the fruit, like that. Okay, so simple as that. Okay, then the fruits are transported in the treadmills, washed very well, and then the residues are discarded in several points that we obtain residues. Here, the piece of we can have not the complete fruit. We can have only the piece of fruit that can be sold for culinary purposes. But normally, this is the packaging of frozen fruits, already frozen. Okay, so we try to make biocomposites. A biocomposite is a material that made from two or more distinct components, with at least one being naturally sourced, combined to create a new material that offers enhanced performance compared to its individual components. We have here different types of biocomposites. Biocomposites or green composites should be fully degradable. That's the definition. That are fully degradable, that are made up of biopolymer matrix and natural fibers as a reinforcing fiber. So biocomposites or green composites are fully degradable composites that are made up of biopolymer matrix and natural fibers as a reinforcing phase. The biodegradable polymers, we can have different sources. We can have biomass products from agro resources, from microorganisms obtained by extraction, from biotechnology obtained with the conventional synthesis from bio-derived monomers, and also from petrochemical products using conventional synthesis from synthetic monomers. Of course, we want to use biomass products rich in the polysaccharides molecules like starch in the left and lignocellulose products. That's our purpose. So, chestnut composition. The fruit is composed mainly by starch, around between the 38 until 63%, proteins between 4 to 11%, and sugars between 7 to 31%. We have also the burr. Burr is composed by lignin and around 24%, and cellulose around 33%. We have internal shell and outside shell, both composed by lignin and cellulose. So for our project of biocomposite production, we have several steps, 3 steps. The first one, the production. It means with a pre-treatment, preliminary tests, and optimization using box banking design. Also the characterization about mechanical properties, wettability, water absorption, thermal conductivity, thermogravimetry, scanning electron microscopy, and also the phytotoxicity. And the application, we have done all this characterization, and we built a customized seed press, and we have produced a candle holder. So for treatment, we use chestnut without any commercial value. We use the chestnut, a very small chestnut, smaller than 20 millimeters, chestnut with hollow nut and rotten fruit. And we submit to a dehydratation at 41 degrees, 48 hours with ventilation. Then ground the chestnut in the 2 millimeters particles, and then we obtain homogenization the pieces. For production, we select the compression molder. The principle of compression molder is a simple process of pressing or squeezing the formable material charged between 2 halves of a heated mold and its subsequent transformation into a molded part after cooling or curing, as you can see in the picture. For preliminary tests, we use a hot compression molding. We use a disc-shaped specimen with around 160 millimeters of diameter, and we use a pressure of 6 tons for 30 minutes. Of course, a lot of parameters should be optimized, like the percentage of chestnut, the percentage of glycerol, of the plasticizer glycerol, the ideal temperature, because we have boundaries between 80 to 120, because above that does not going well. And we evaluate the composites using 2 properties, the flexural strength and models of elasticity. So response surface methodology with box bank design was used to investigate the influence of the independent variables, which comprise the chestnut content, glycerol content, and molding temperature on the flexural strength and flexural models. This table on the middle shows the design metrics for 17 experimental runs. Each run was performed in triplicate, and here in the right, this is the picture of the 17 biocomposites obtained. We have evaluated, as already told, the flexural strength, also referred as models of rupture, is a material property that measures the maximum stress a material can withstand just before failure into a flexural test. Flexural models is defined as a measure of stiffness during the initial bending process. The table on the left presents the experimental and predicted values for both response used to optimize the chestnut-based composite. So flexural strength and flexural models have the same unity. As observed in the figure in the right, there is generally a reasonable agreement between the experimental and predicted values for both the response in the left flexural strength and right the elastic models. However, the elastic models shows a better adjust than the flexural strength. So here is a quadratic model, was evaluated for both properties. Chestnut shows no clear correlation with either flexural strength or elastic models across the experiment. However, the impact of glycerol on the flexural strength appears to be inversely related. Lower concentration of glycerol, as you can see, tend to enhance the flexural strength. About the temperature variation play a critical role in determining flexural strength, with a direct proportionality between temperature and flexural strength was observed. Considering that the quadratic model didn't show a very good adjustment to experimental values, a linear model was done without the variables that didn't show considered influence. Based on ANOVA analysis of variance results for the modified linear models of flexural strength, only the glycerol and temperature show very strong evidence of the response, indicating that glycerol content and temperature play crucial roles in flexural strength. The model itself was highly significant, providing very strong evidence of the fit model. So we obtained this equation to explain, to determining the best biocomposite to obtain the best flexural strength. Regarding the elastic models, the model was optimized by eliminating the irrelevant variables, resulting in this equation, which include, as you can see, a second-degree interaction. As can be seen in the 3D graph, we have higher elastic models with low concentration of chestnut and low concentration of glycerol. So with the all this data, we obtained the best composition for the biocomposite. For flexural strength, using the equation, is 75% of chestnut, 0 without glycerol, and the molding temperature is 120. For elastic models is 67% of chestnut without glycerol, and the molding temperature is 118. So for considering these two properties, was decided to use 70% of chestnut without glycerol and 120 of molding temperature. To improve water resistance of the biocomposite is necessary to use a resin. So shellac is a natural resin, is obtained from tiny insects from curious species feeding on the sap of specific host trees. In its basic form, shellac is a polyester macromolecule composed of esters of polyhydroxyaliphatic and sesquiterpene acids. Shellac is a general recognized as safe polymer. So we use shellac. The solution was shellac solution was applied evenly with a brush to the selected biocomposite, and we obtain this like this. About wettability is the ability to a liquid to maintain contact with a solid surface. And it is controlled by the balance between the intermolecular interaction of adhesive liquid to a surface and cohesive liquid to liquid type interface. So in here in the picture, above you can see high surface tension, no wetting, and lower this kind of drops you can have low surface tension wetting. So we use a drop of distillated water was placed in the surface of the composite, and the angle formed between the drop and the material was measured. The effect of adding shellac on the right as a hydrophobic surface coating was studied by comparing one composite with shellac with another one without. The results show that the untreated composite had a higher contact angle. In the left, the angle was 72, compared to the composite treated with shellac that obtained 43 the angle. This suggests that the shellac-treated surface was more hydrophilic, contrary to initial expectation that shellac would enhance water resistance. A possible explanation for this outcome is that is the effect of shellac on fiber orientation. As you can see, fiber stands more upright without shellac, creating a textured surface that may repel water more effectively. Fiber align more flatly with shellac, resulting in a smoother surface that reduces water repellence. Despite these findings, both composites surfaces are classified as hydrophilic. Water absorption, we also evaluate water absorption. In composite materials, particularly those with natural fibers, can lead to a decrease in their mechanical properties. This is because water can penetrate the composite, causing swelling, weakening of the matrix fiber interface, and even degradation of the matrix, as you can see on the right. Biopolymers materials is known to be very subtle to water. Therefore, it is important to investigate the water absorption properties of the total bio-based materials prepared in this study. So, water absorption, we evaluate the composite composed only with the chestnut with glycerol, and chestnut with shellac. We use this equation to evaluate the water absorption. So, water absorption tests reveal that biocomposites without glycerol, only chestnut, absorb 10% of water after 2 hours, increasing to 45 after 24 hours, reaching about 60% at 96 hours to the hydrophilic nature of starch and fibers. Composites with glycerol show even higher absorption, surpassing 65% at 96 hours, attributing to glycerol moisture attracting properties. Shellac-treated composites demonstrated the lowest water absorption, approximately 30% at 96 hours, showcasing shellac's effective water resistance. The thermal conductivity of biocomposites is a crucial parameter that affects their suitability for various applications, particularly in insulation and energy-efficient designs. Factors influencing thermal conductivity in biocomposites include materials density, moisture content, and type and orientation of reinforcing fibers. We use homemade equipment to evaluate thermal conductivity, and our chestnut-based composite exhibit a thermal conductivity of 0.79 watts per meter Kelvin after 53 minutes at 48 degrees, categorizing this biocomposite as a thermal insulator. We evaluate our biocomposites by thermal gravimetry and differential scanning calorimetry. We use these experimental conditions. So A and C are thermograms obtained from biocomposites with only chestnuts. B and D are thermograms from biocomposites with glycerol. As you can see, the C and D thermograms showing the first derivative of thermogravimetry curve, revealing the different rate of weight change with respect to temperature. Thermogram B show a similar initial loss, similar to A. The initial moisture loss at around 81 degrees. Within the main decomposition, slightly shifted to 317 degrees, indicating a minor stabilizing effect from glycerol. Also in thermogram A, only with from the biocomposite composite with only chestnut, as you can see, has a higher hash residue at around 31% compared to B, suggesting glycerol facilitated a more complete combustion. All data of this work are described in this manuscript from Polymers. We also evaluate the biocomposites by scanning electron microscopy to observe the morphology. So as you can see, we have different magnification. At here we have 400, 110 micrometers. As observed, the composition of our biocomposites includes fibers isolated from chestnut shell that act as a reinforcement agent. of the polymeric matrix composed also of starch granules, as you can see in C picture, with an average diameter of around 6 micrometer. We also evaluated the phytotoxicity of our biocomposites. We use these to prepare the leaches. We use these Swedish standards that is in the picture. In here, the biocomposite samples were cut in approximately 4 millimeter pieces. Then the material were placed in a flask with the deionized water. The control was sterile water without samples. Each treatment was carried out in triplicate. The flasks were wrapped in aluminum foil and agitated at 95 RPM for 72 hours at 24 degrees. After agitation, the leaches were obtained by a 0.45 micrometer pore size filter, and then the phytotoxicity were evaluated. The phytotoxicity in biocomposites refers to the treatmental effect that certain substances within a biocomposite material can have on a plant growth or development. For that study, we use 5 types of species, and we use 6 seeds in each petri dish. Then we use or deionized water or the leaches from biocomposites previously obtained in here. The petri dish was sealed with parafilm to minimize evaporation and incubated in darkness at 25 degrees for 72 hours in a climate control chamber. According to EN standards, control test sample must achieve at least 70% of seed germination, and we evaluate the germination of all seeds here, and then take picture of every petri dishes. After in petri dish, we evaluate the germination, but we also evaluate the root elongation and shoot length. For that, we use software, in this case, the image G software to, in this case, as you can see, we are evaluate the root elongation, but same for shoot length. After all tests were performed, we developed a hydraulic press to produce a candle holder, and light was made, as you can see. We produce this candle holder using a composite with 75% of chestnut, treated with shellac and processed at 120 degrees, and the glycerol was excluded. This pioneer prototype illustrates the practical application of these research findings, showcasing how chestnut waste can be transformed into a functional product, emphasizing sustainable practice in waste valorization. This study underscored the viability of incorporating natural materials into functional products, offering an environmentally friendly alternative to fossil-based plastic and contributing to sustainability. Thank you very much for your attention, and please take a minute to evaluate this lecture. You can do that using this QR code. Once again, Thank you very much.